In computer science, a rough set, first described by Polish computer scientist Zdzisław I.Pawlak, is a formal approximation of a crisp set in terms of a pair of sets which give the lower and the upper approximation of the original set. In the standard version of rough set theory, the lower and upper approximation sets are crisp sets, but in other variations, the approximating sets may be fuzzy sets. Definitions. The following section contains an overview of the basic framework of rough set theory, as originally proposed by Zdzisław I.Pawlak, along with some of the key definitions. More formal properties and boundaries of rough sets can be found in Pawlak and cited references. The initial and basic theory of rough sets is sometimes referred to as Pawlak rough sets, or classical rough sets, as a means to distinguish from more recent extensions and generalizations. Information system framework. Let be an information system, where is a non-empty set of finite objects and is a non-empty, finite set of attributes such that for every is the set of values that attribute may take. The information table assigns a value from to each attribute and object in the universe. With any there is an associated equivalence relation. The relation is called a indiscernibility relation. The partition of is a family of all equivalence classes of and is denoted by if, then and are indiscernible by attributes from. Example. Equivalence class structure. For example, consider the following information table. When the full set of attributes is considered, we see that we have the following 7 equivalence classes. Thus, the 2 objects within the first equivalence class cannot be distinguished from each other based on the available attributes, and the 3 objects within the second equivalence class cannot be distinguished from one another based on the available attributes. The remaining 5 objects are each discernible from all other objects. The equivalence classes of the indiscernibility relation are denoted. It is apparent that different attribute subset selections will in general lead to different indiscernibility classes. For example, if attribute alone is selected, we obtain the following, much coarser, equivalence class structure. Definition of a rough set. Let be a target set that we wish to represent using attribute subset, that is, we are told that an arbitrary set of objects comprises a single class, and we wish to express this class using the equivalence classes induced by attribute subset. In general, cannot be expressed exactly, because the set may include and exclude objects which are indistinguishable on the basis of attributes. For example, consider the target set, and let attribute subset the full available set of features. It will be noted that the set cannot be expressed exactly, because objects are indiscernible. Thus, there is no way to represent any set which includes but excludes objects and, however, the target set can be approximated using only the information contained within by constructing the lower and upper approximations of lower approximation and positive region. The lower approximation, or positive region, is the union of all equivalence classes in which are contained by the target set. In the example, the union of the 2 equivalence classes in which are contained in the target set. The lower approximation is the complete set of objects in that can be positively classified as belonging to target set. Upper approximation and negative region. The upper approximation is the union of all equivalence classes in which have non-empty intersection with the target set. In the example, the union of the 3 equivalence classes in that have non-empty intersection with the target set. The upper approximation is the complete set of objects that in that cannot be positively classified as belonging to the complement. The upper approximation is a liberal approximation which includes all objects that might be members of target set. From the perspective of the lower approximation contains objects that are members of the target set with certainty, while the upper approximation contains objects that are members of the target set with non-zero probability. The rough set. The tuple composed of the lower and upper approximation is called a rough set. Thus, a rough set is composed of 2 crisp sets, one representing a lower boundary of the target set, and the other representing an upper boundary of the target set. The accuracy of the Rouse set representation of the set can be given by the following. That is, the accuracy of the rough set representation of is the ratio of the number of objects which can positively be placed into the number of objects that can possibly be placed in. This provides a measure of how closely the Rouse set is approximating the target set. Clearly, when the upper and lower approximations are equal, then, and the approximation is perfect, at the other extreme. Whenever the lower approximation is empty, the accuracy is 0. Objective analysis. Rouse set theory is one of many methods that can be employed to analyze uncertain systems. Although less common than more traditional methods of probability, statistics, entropy and Dempster-Shafer theory. However, a key difference, and a unique strength, of using classical rough set theory is that it provides an objective form of analysis. Unlike other methods, as those given above, classical Rouse set analysis requires no additional information, external parameters, models, functions, grades or subjective interpretations to determine set membership. Instead, it only uses the information presented within the given data. More recent adaptations of rough set theory, such as dominance-based decision theoretic and fuzzy rough sets, have introduced more subjectivity to the analysis. Definability. In general, the upper and lower approximations are not equal. In such cases, we say that target set is undefinable or roughly definable on attribute set. When the upper and lower approximations are equal, then the target set is definable on attribute set. We can distinguish the following special cases of undefinability. Set is internally undefinable if an. This means that on attribute set, there are objects which we can be certain belong to target set, but there are no objects which we can definitively exclude from set. Set is externally undefinable if an. This means that on attribute set, there are no objects which we can be certain belong to target set, but there are objects which we can definitively exclude from set. Set is totally undefinable if an. This means that on attribute set, there are no objects which we can be certain belong to target set, and there are no objects which we can definitively exclude from set. Thus, on attribute set, we cannot decide whether any object is, or is not, a member of reductant core. An interesting question is whether there are attributes in the information system which are more important to the knowledge represented in the equivalence class structure than other attributes. Often, we wonder whether there is a subset of attributes which can, by itself, fully characterize the knowledge in the database. Such an attribute set is called a reduct. Formally, a reduct is a subset of attributes such that equals, that is, the equivalence classes induced by the reduced attribute set are the same as the equivalence class structure induced by the full attribute set. The attribute set is minimal, in the sense that for any attribute, in other words, no attribute can be removed from set without changing the equivalence classes. A reduct can be thought of as a sufficient set of features, sufficient, that is, to represent the category structure. In the example table above, attribute set is a reduct. The information system projected on just these attributes possesses the same equivalence class structure as that expressed by the full attribute set. Attribute set is a legitimate reduct because eliminating any of these attributes causes a collapse of the equivalence class structure, with the result that the reduct of an information system is not unique. There may be many subsets of attributes which preserve the equivalence class structure expressed in the information system. In the example information system above, another reduct is producing the same equivalence class structure as the set of attributes which is common to all reducts is called the core. The core is the set of attributes which is possessed by every legitimate reduct, and therefore consists of attributes which cannot be removed from the information system without causing collapse of the equivalence class structure. The core may be thought of as the set of necessary attributes, necessary, that is, for the category structure to be represented. In the example, the only such attribute is, any one of the other attributes can be removed singly without damaging the equivalence class structure, and hence these are all dispensable. However, removing by itself does change the equivalence class structure, and thus is the indispensable attribute of this information system, and hence the core. It is possible for the core to be empty, which means that there is no indispensable attribute. Any single attribute in such an information system can be deleted without altering the equivalence class structure. In such cases, there is no essential or necessary attribute which is required for the class structure to be represented. Attribute dependency. One of the most important aspects of database analysis or data acquisition is the discovery of attribute dependencies, that is, we wish to discover which variables are strongly related to which other variables. Generally, it is these strong relationships that will warrant further investigation, and that will ultimately be of use in predictive modeling. In rough set theory, the notion of dependency is defined very simply. Let us take two sets of attributes, set and set, and inquire what degree of dependency obtains between them. Each attribute set induces an equivalence class structure, the equivalence class is induced by given by, and the equivalence class is induced by given by. Let, where is a given equivalence class from the equivalence class structure induced by attribute set. Then, the dependency of attribute set on attribute set is given by, that is, for each equivalence class in. We add up the size of its lower approximation by the attributes in, i.e., this approximation is the number of objects which on attribute set can be positively identified as belonging to target set, added across all equivalence classes in. The numerator above represents the total number of objects which, based on attribute set, can be positively categorized according to the classification induced by attributes. The dependency ratio therefore expresses the proportion of such classifiable objects. The dependency can be interpreted as a proportion of such objects in the information system for which it suffices to know the values of attributes in to determine the values of attributes in. Another, intuitive way to consider dependency is to take the partition induced by Q as the target class C, and consider P as the attribute set we wish to use in order to reconstruct the target class C. If P can completely reconstruct C, then Q depends totally upon P. If P results in a poor and perhaps a random reconstruction of C, then Q does not depend upon P at all. Thus, this measure of dependency expresses the degree of functional dependency of attribute set on attribute set. It is not symmetric. The relationship of this notion of attribute dependency to more traditional information theoretic notions of attribute dependence has been discussed in a number of sources.